Build a KNN classifier in Python today. By the end, you will rank neighbors by distance, predict a class with simple voting, and wrap the logic into a reusable function to classify new points. You will also see how the choice of K and distance weighting changes results. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. KNN is a similarity-first method. It answers the question, which labeled points are closest to my query? People reach for it when they want something simple, interpretable, and quick to prototype. The trade-off is prediction cost. You store the training set and compare the query to every point. That works fine for small and medium datasets, but becomes slow at large scale. Pi-dimensional data also blurs distances, which can reduce accuracy compared to learned models. Think of it like classifying colored dots on a plane. A new dot looks around at its nearest neighbors and adopts the most common color. The strength is transparency. You can point to the exact neighbors that decided the label. The weakness is that noisy or outlier neighbors can mislead the vote, and nearest neighbors change with K. We will use a tiny, two-dimensional toy dataset, so the ideas are visible and easy to follow. We will build a small script that ranks distances, shows majority voting, compares different K values, demonstrates distance weighting, and then classifies a few new queries. This snippet sets up 4 two-dimensional points with labels and a single query, then computes distances to rank them. The function hypot is used, which computes Euclidean distance without manual squares and square roots, so the code stays simple and clear. The snippet builds a list pairing each index with its distance to the query, sorts that list so the closest points come first, and extracts the top 3 neighbors with distances rounded to 2 decimals for readability. The printed output names which points are closest and by how much, grounding the nearest neighbor intuition in a concrete example. Now we'll predict the label using majority voting. This snippet reads the sorted distances and performs a simple K nearest neighbor vote to predict the class for the query. It slices the first K neighbor indices and uses Counter, which tallies items and returns counts, to count labels among those neighbors and select the most common label. The result is stored in a variable called pred and printed as the classifier's decision for that query. If you increase K, the prediction generally smooths and becomes less sensitive to a single neighbor. Decreasing K makes the decision react more sharply to the closest point. Now we will compare predictions across different values of K. This snippet runs the same query through several K values and collects the predicted label for each. It defines a list of K values and for each one slices the K nearest indices and computes the majority label using Counter. The outcome is a small mapping from each K to its predicted class, so you can see if the decision is stable or flips as K changes. This helps you understand sensitivity. Larger K averages over more neighbors and can wash out local structure, while smaller K can capture very local patterns but be noisier. Next, we'll contrast plain voting with distance-weighted voting. This snippet uses 4 neighbors and compares unweighted majority voting to a distance-weighted vote that favors nearer neighbors. Unweighted counts can produce ties, so the code shows either the top class or a tie result. The weighted approach accumulates per-class scores using 1/distance so that closer neighbors contribute more influence. Selecting the class with the largest weighted sum often breaks ties and better reflects proximity. Increasing K in this setting makes ties more likely in simple counts, while weighting tends to preserve the influence of very close points without changing the underlying data. Finally, we'll wrap the process into a reusable predict function and classify multiple queries. This snippet packages the KNN logic into a predict function that accepts a query and a neighbor count K, builds distances from the query to all training points using hypot, sorts them, and returns the majority label among the k closest. Encapsulation avoids repeating sorting and counting code, and makes it easy to call the same logic on many queries. The snippet defines a list of new queries and uses a list comprehension to collect predictions. Lower k values make the output more sensitive to each query's nearest point, while higher k values yield more stable classifications. Recap: KNN finds the closest training points and votes to label a query. Use it for small to medium datasets where interpretability and quick prototyping matter. Caveat: it costs more at prediction time, and distances can become less meaningful in high dimensions. Next step: try swapping Euclidean distance for cosine similarity in the same pipeline to see how angular similarity changes neighbor choices and classification stability. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.